Well, hello everybody. Exciting day. We are just about near the end of me talking. Okay. Uh, we're going to get right into it and start talking about how we actually use the Kalman filter in this class with respect to satellites. There's not a lot of not a lot of goofing off today because it's a fairly short lesson, and as far as our attention span goes, this is pretty much the list of what you need for the project. So uh, and it's not a lot of background derivations. So you should be fairly motivated. All right. All right, so let's just see if we can put all of this in one page here in the very, very general Kalman filter sort of algorithm. Okay, first thing you got to do is initialize things. So we're going to find our guess at the solution at epoch. All right, that's 0.0, and that's the Harrod-Gibbs, just like you've already been doing. All right, we're going to set the covariance matrix to something really big. That's our initial covariance matrix, because we haven't been able to calculate one yet. We haven't done a step. And we're going to make it really big because the covariance matrix, remember, is telling you how good your solution is. And so we haven't even started yet, other than Harrod-Gibbs, and we don't think that that's going to be so great. So we want the covariance matrix to be really, really big. We don't trust it at all. Then we'll go ahead and get to our first data point, k plus 1, 0 plus 1, observation 1. All right, read that in. Then we're going to go into predict mode. We predict state vector at k plus 1 using our epoch guess. And that's just cowl. We propagate what we think it should be at observation 1. Then we do this. We propagate our state correction to observation 1, the del x hat. And then we do the same for the covariance matrix. We have this wild big guess of what it is at the Harrod-Gibbs epoch, and we just propagate that forward in time. All right, so far we haven't used anything new. We've read in the observation, I guess, but the predictions are just based on the last step. Then we go into correct mode. Right, we create our residual matrix, the B tilde, based off of our prediction and what we actually observed. We compute the correction. Okay, so now we're computing it. We're not propagating it and estimating it. We are computing the correction, the del x hat. We compute the covariance at the k plus 1. And then we apply the correction that we've calculated, adding that to the state vector. And now we have a better approximation of the state. And then we just go loop back and get another point and keep doing that. So that's a very generalized sort of algorithm for a Kalman filter. What I want to do is visualize this a little bit. All right. So this is just the general process. All right, and we'll get into more specifics, of course, here in 5 or 10 minutes. But visually, what I'm doing here is, let's say I have 3 observations, okay? And somehow I came up with, ooh, where's my pen? There we go. All right. Okay, so I've come up with a guess at the solution, but I haven't actually used any of the data yet. I kind of have because Harrod-Gibbs used some data, but however you get your guess, you wouldn't necessarily have used the data. All right, and if that state is true, then it would give me a reference trajectory, what we'll call a reference trajectory. And we see that that reference trajectory isn't very good. It doesn't really match the data points very much. Okay. So what we do is we take this and we predict all those things for observation 1. All right, and then after we do our math, we have a correction, del x hat, that would incorporate observation 1. Then we get a second observation and we go into predict mode. So I've taken this actual del x hat and predicted it in the future what it would be at observation 2. And then I go into correct mode based on what I'm actually seeing, and I get an actual del x hat for observation 2. How I would need to correct this reference trajectory, reference solution, to get a trajectory that fits the data. But in the general sense, I don't actually need to do a correction here. I can just keep track of this running del x hat, the correction that I would need to make to this reference trajectory. Okay, so then observation 3 comes in. I take this del x hat. I say, what do I think it would be at observation 3? And then I use that with all my linear algebra, and I get a corrected del x hat. And so in the general sense, I'm not actually applying the correction. I'm just keeping an improved correction, and I could stop it pretty much any time I want and find the actual state vector or COEs. But I don't really have to do that every step. I'm just finding an improved correction as we go. Okay. Right. Now with the extended Kalman filter, that's more the big picture that we've been working towards. We're going to use Kalman filter, and it's going to be a type of Kalman filter that actually turns out easier for us, and it's an extended Kalman filter, and that's the algorithm we're going to be talking about today. So how does it work? Okay, so you start off the same way. You have some data, some observations, but you haven't used them yet. You have some sort of guess at epoch that gives you a reference trajectory, which isn't that good. And you do your calculations, including observation 1. You get a del x hat, a correction to your initial guess at observation 1 that would give you a better fit to the data you've looked at so far. Okay. Now what we're going to do is actually, at observation 1, apply that correction, and now instead of the reference trajectory, we have an updated trajectory. And you can see that it fits observation, our guess, and observation 1 a lot better. Hasn't looked at 2 and 3 yet. Right? And so then what you do is the same sort of procedure. You're going to propagate stuff into the future. However, here's where it gets neat. Since we have applied the correction, there's no correction to propagate. We've already made the correction. If we had some idea of a correction here, we would have applied it already. So the del x hat that we're propagating is 0 times some state transition matrix, so it doesn't happen. So we don't have to worry about that. So all we're doing now is looking into the future and finding the del x hat to this new trajectory and then applying that. And then that'll update us there. So some neat things you could do here, if you just kind of think about the power of this as opposed to just taking all your data and doing a least squares fit. Each time I got to an observation and figured out what the updated state vector was, or the COEs, I could write them down. All right, and then I go to observation 2. What do I think my COEs are? I could write it down. Okay, and not just because I updated it here, I might not, let's say that we don't go back and update what it should have been at observation 1. We're just writing down what it is. All right, and so as you go, and you're writing these down, let's say the semi-major axis was decreasing faster than we thought it should. Well, what that tells us, it gives us some time information about this instead of just, like I said, doing a fit to all the data. Semi-major axis going down faster than we thought it would. Now, why would that happen? We're accounting for drag. That's why semi-major axis would decrease, but we're using a model, right? So what that would tell me is that my model is not giving me enough drag. The atmosphere is actually thicker than the model, because we know that the atmosphere changes solar cycles and all sorts of stuff, but that Atmos 76 doesn't. And so it's telling me model errors. Or you can kind of work that backwards. You can talk to Dr. Dahlke more about this, but he's done some work where I guess there's 3 satellites in orbit that are just spherical aluminum balls, and they're at slightly different altitudes. Okay, and so you can do this sort of prediction, this Kalman filter, and compare what's happening to what's actually happening, and get a better model of the density of the atmosphere with time. See what the drag actually was instead of just a prediction. So that's one example of how you could use this to do some deep stuff. All right. So let's actually see how we're going to program this. First thing you're going to do is initialize. Okay, so the initial state vector guess at epoch, x bar naught, and you get that from Herod-Gibbs, right? So that's easy, nothing new there. The initial state correction, well, it's del x hat initial is 0. If I already had a guess on like how I need to correct this, then I would have done it. We have no information on that. Herod-Gibbs, we have no del x hat to add to that right now. All right, so set that to 0. And then you set the covariance matrix really big. Now, we don't want to use the INF, the infinity, because crazy things can happen. But since we don't trust our initial Herod-Gibbs covariance at all, we're going to use 9 times 10 to the 5th times the identity matrix. So as we start marching through observations, this Herod-Gibbs is pretty much going to get thrown away pretty quickly. Just a starting point. All right, so that's up front, initialization. We're going to read in our new data point, our observation, and that'll be y sub observation at k plus 1. So if we started at 0, we're now at observation 1. And so you apply the rho as L biases. Remember, the observations come in rho as and L. Apply the biases just like you're already doing. Then we go into predict mode. All right, you're going to find psi, the psi matrix. Remember, you need the F for that and a delta T. You can, in the folder in our file section, I've uploaded a document that is pretty much a summary of the equations. Might be useful if you don't want to scan through the videos here. So what we got to be careful with is time. Where are we at? Where did we just come from? Keeping all that straight. We're not going back to epoch every time now. Some of y'all wanted to do it this way with LSDC, and that wouldn't work. We always have to keep going back to epoch and then propagating from epoch to the observation. But now you can do what you initially wanted to do if you were in that group. We're going to base our delta T off of the time that's elapsed since the last observation. Okay, so if we know observation 5 and we've already crunched all that, and now observation 6 comes in, the delta T is the time between 5 and 6. And the F matrix that we need to calculate, we're using the R from the last observation, right? For that F is telling us the partial of accelerations with respect to position. So yeah. We need to predict the new state. All right, for the observation that just came in, and so that's cal, and you're going to propagate it from the last observation where you updated your state vector. Now, in the general sense of the Kalman filter procedure, we would now predict the state correction. But you don't need to do that because you made it at the last observation, so there's no state correction left. It's 0. So 0 times all these matrices is just 0. So you can do it if you want, but you don't actually need to predict the new state correction. You do need to predict the new covariance. Okay, so you are using this equation here, state transition matrix and the last covariance matrix. Q is a tuning matrix. Remember that sometimes these solutions can get smug. So if the covariance was getting really small, then this would all start getting small and you wouldn't really be incorporating new data very well. So this Q keeps your predicted covariance matrix from ever getting near 0. For this application, we'll assume that Q is 0. We don't need a tuning matrix. Then, last slide, we go into correct mode. Okay, so you're going to produce your calculated rho as L for the new observation, using rho as L for that and the predicted state. You're going to compute the residuals, B tilde, what you think it should be versus what you just saw. You're going to construct an H and an H transpose using the currently predicted R. Remember that this H is kind of replaces our A, where we're finding sensitivities. How do my observations change if I adjust the X, Y, and Z? Except this was even easier to build because there are no dependencies on velocities if we're talking about right now. So we need to use that R that we've predicted right now. And then you're going to compute the Kalman gain. There's your equation for that. You're going to compute the new state correction, which here's the equation for that. But look what's really neat. Since we updated everything at our last observation, there is no, the expected update, del x bar, is 0. Okay, so that's a 0. That's a 0, and this all just comes down to our new state correction being equal to k times b tilde. So yay. All right. Then we compute a new covariance matrix using this equation. Then we compute the new state vector by taking what we thought it was and adding what we just calculated our correction to be using the observation. And boom, now we have an updated state vector at this new observation time. And then you just read another observation and go there. All right, so that's all a lot easier said than done. But that is what you want to print out and keep checking yourself and see if you did it. So as far as the next project, EKF, you have everything from me that you need. Obviously, you don't want to start from scratch on this. Make a copy of your LSDC and then methodically go through each step in this algorithm and see where you need to do something new and where you don't need to do stuff. For instance, building the A matrix, you had to do cowl 9 times, but now you don't. You just do that one cowl to get you a predicted state at the new observation. You might want to do some subroutines for this. This is really going to be where the good programmers that kind of took to heart stuff since 201, laying out good algorithm and subroutines when they needed it, subfunctions when they needed it. It's going to be a pretty straightforward expansion into this, following the LSDC. Now, if you were just pounding at LSDC and it was just a big mess until you finally got something that looked like you could turn it in, then now modifying it might be a little harder for you because you don't really know what's doing what that well. But anyway, we've got the rest of the semester to figure it out. So with that, I will conclude today.